I'm excited about this next problem. All right. Okay, because not only does it utilize pressure, so we got a KP we got to use, nice. It also utilizes a concept that we learned in chemistry 1. Yes, called Dalton's law. Yes, yes. Okay, all right. Oh, just want to point something out. If you're keeping track at home, the topics we've covered, I've actually gone through all this stuff right down. We're just about to do what are called ice charts, and I put a star there. They're really important. This is not an ice chart problem, but we've done all of this stuff here. One thing I just didn't mention was heterogeneous and homogeneous equilibrium. That's easy. What that means is if it's heterogeneous equilibrium, you have different phases involved in the reaction. If it's homogeneous equilibrium, you have the same phase involved in the reaction. So you can see I gave you an example here of heterogeneous equilibrium, where you've got your solid, and a gas. They're different. And homogeneous equilibrium would be one where you have all gases, like that one. All right. So other than that, we've covered all of this stuff. Actually, we just finished doing our K's and our Q's. Okay, so Q's and K's. All right. This problem's awesome. I know you might not think it's awesome, but I hope you think it's awesome, because I think you're all awesome. And if you're all awesome, you'll think it's awesome. This problem says, calculate the pressure of the nitrogen monoxide and the nitrogen dioxide in the mixture. So we're given one pressure, and we're given a K value. Many times in chemistry, you're given, a lot of times it seems like we're doing this to find K values. Actually, no, it's the opposite. What you're usually given, or you can look up, because there are tables of K values at particular temperatures, you can look those up. You use the K value to solve for the concentration of something else. That's usually the way we do it. And we're going to do that in this problem too, but solve for the pressures. So in this problem, we're given the K value for this reaction. We're given the K is 100 and nuts, I forgot, 58? 158. Okay, we also know one other thing. I'm told that the pressure of the oxygen, all right, there it is 0.25 atmospheres. So I know the pressure of this is 0.25 atmospheres. Okay, I'm going to utilize something called Dalton's law. Dalton's law of partial pressure. Quick review. I have a container with a lid on it. I have gas A. It's the purple gas. I have gas B. The green gas. I don't know if you can see that or not. I have 6 purples and 3 greens. We'll say the pressure is a total of 9 atmospheres. We'll make this easy math. So 6 purples, and I have 3 greens in there, and the total pressure is 9 purple and green. That makes sense, right? I mean, the total pressure, that's what Dalton's law says. Dalton's law is very simple. Dalton says that the pressure of a system is equal to the pressures of the individual parts all added together, the partial pressures. So, all right, so if I have 6 purples and 3 greens, well, this must be contributing twice the amount of pressure, because it's twice the amount of gas. So another thing about Dalton's law, very simple, is it says that if you have twice as much of a gas, it's going to contribute twice the pressure. See what I'm getting at here? If I know that this 1 molecule of oxygen provides 0.25 atmospheres, then the two, and these also mean moles too when we're talking about moles. 1 mole provides this, 2 moles should provide what? Twice as much. I already have half the problem done. Oh, this is easy. So that means that if the 1 oxygen provides 0.25, the 2 nitrogen monoxide should provide 0.50 atmospheres of pressure. Oh, so this is super easy. We're done basically, because this is 2 as well. So this one will provide twice that and provide 0.5 as well. We're all done. No, you can tell by the voice and the sarcasm that no, Billy, no. This is in equilibrium. We don't know whether or not we have more of this or more of that. We don't know if products are favored or not, but we can figure that out. Look, K value is 158. Remember, this chemistry should make sense, I hope. This means that these are favored. There's more of this than there is of this. That's what that means. There's more, higher than 1, of this than there is of this. That means there's not a lot of this, which means it's not going to provide very much pressure. We can use Dalton's law and logic on the right. We cannot use it on the left because we don't know how much of this there was and how much of it's breaking down. All I know is there's more of this than this. So in equilibrium, this third gas in here, maybe I'll make it the red. I don't know how much of it is. There is a 1 dot. Is there 2 dots? I don't know. We got to figure out how many dots. Now, when I say dots, I mean pressure. Okay, so easy solution on the right, not as easy on the left. So let's go ahead and calculate our Kp, because we have pressures set up at Kp. So Kp equals the pressure. Now, there are two products. So the pressure of nitrogen monoxide squared multiplied by the pressure of the oxygen divided by the pressure of the nitrogen dioxide squared. There's my setup. All right, let's throw things in. We have everything. This is not going to be hard. This K is 158. We got that. That's the K. That's the K value. It's Kp. Also, we have the nitrogen monoxide pressure is 0.5. So that's 0.5 squared multiplied by the pressure of the oxygen, 0.25, divided by pressure of the unknown. We don't know the pressure here. That's what we're trying to figure out. So that is my unknown. Call that X. Oh, gotta be careful. Ooh, 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 ooh. Almost missed that. Squared. All right, solve for X. Do it now. Get through the chopper. All right, so I'm gonna bring X squared up here. Let's set this up first. X squared, I'm gonna switch these, cross multiply. So X squared equals, well, let's go ahead and do 0.5 times 0.5. That should be 0.25. 0.5 times 0.5 should be 0.25, which it is, 0.25. So 0.25, 0.5 times 0.5 is 0.25 times 0.25. So this equals 0.25. Then you have to multiply again by 0.25. So that's 0.0625. Divided by, remember I'm going to switch this, 158. Whoops, that is not a good value. 158. Now that was X squared. So I don't want X squared, I want X. How do you get rid of the square? Square both sides. Square root both sides. Square rooting is squared gets rid of the square, and square root the other side. What you do to one side, you got to do the other. Square root both sides, that goes away. Now I've got my setup. All right. I hope you remember that math. If you have a square, you don't want it there, take square root of it, but you have square root the other side as well. Okay, so let's see. 0.0625 divided by 158. I'm going to take the square root of that. Second function square root. Second function answer. And we get 0.0198. I'm going to call that 0.019888889. 0.02. All right, 0.02. 0.02. Now remember what we were calculating. Well, first of all, let's just make sure it's right. Okay, 0.02. Yep, there it is. We're good. We're good. 0.02. So that is the pressure that this gas, remember we were figuring out. We were figuring this out. So this is atmosphere. This gas here, the nitrogen dioxide, provides 0.02 of it. Now I hope that makes sense because this this hardly provides anything at all. There's not a lot of pressure provided by this because we don't have a lot of it. If we don't have a lot of it, it can't provide a lot of pressure. How do you know you don't have a lot of it? The K value is big. That means there's more of this. That's what the K value means. K value big, there's more product. There's more of this than this. So it all makes sense. The K value predicted that I should not have much of this, and I don't because it doesn't produce a lot of pressure. All right, see how good chemistry is? It's so fun.